Okay guys, you are going to use this video to help you to complete your notes for today. So you'll go through the Edpuzzle, and as you're going through the Edpuzzle, it'll have you pause and fill out the notes. Some of the slides will require notes, some of them not, and I'll kind of let you know as you go through each one. All right, so we're going to start out with the 5 points of the kinetic molecular theory, which have to do with the properties of an ideal gas. So our gas laws unit is obviously talking about gases and mathematical formulas to identify different properties. And for these formulas and for this unit, we're operating using the kinetic molecular theory. So remember, kinetic is energy of motion. And so these are just some of the things that we're assuming are true when we are using these 5 different formulas that we're going to use in this unit. So first of all, motion. Here we have, with motion, gas particles are in constant random motion and move in straight lines between collisions. So one of the things I want to point out is that they're not necessarily moving straight up and down or straight left and right. They can move at angles, but when they start to move, they don't swerve like this, you know. So just once they move in a straight line until they bounce off something else. We've talked about volume a little bit when we've talked about our mole conversion, 1 to 22.4 liters, right? So the idea with the kinetic molecular theory and volume is that each molecule of the gas, no matter what kind of molecule it is, it behaves like this tiny single point. And that tiny single point or molecule within the gas is has very, very little volume compared to the overall volume of the gas. And point 3 is that when you have a couple of different of these gas molecules, you're going to find out later that molecules can kind of attract or repel each other, while in an ideal gas, the assumption here is that they are not attracting or repelling each other. It's just random motion that makes them bounce off of each other. The last 2 points of the kinetic molecular theory are that collisions are perfectly elastic, which means that they collide and bounce back and no kinetic energy is lost or transferred from one molecule to the next. So all energy is conserved. And then finally, the average kinetic energy of a gas sample is proportional to its temperature in Kelvin or degrees Celsius. And so that's something that's pretty true always. And this just kind of shows you the same gas. If we have a lower temperature, right, then you're going to have lower average kinetic energy. That means most of the molecules are going to kind of fall over in this low kinetic energy. And then when you have a higher temperature, this red dotted line here is representing that same gas. So there's less molecules at the lower temperature and more molecules at a higher average kinetic energy. So you have warmer and overall warmer gas. So those are our 5 points of the kinetic molecular theory. Make sure you fill that information in. Okay, these are our units and variables that we're going to be using in our different equations. P is equal to pressure, V is volume, N is moles, T is temperature, and R is our gas law constant. You'll see STP come up occasionally, and that is standard temperature and pressure. We've already learned about that. That is 0 degrees Celsius or 273 degrees Kelvin. We'll typically use that one. And 1 atmosphere of pressure. We're not going to be using the gas law constant until our very last, our 5th ideal gas law. We're going to be focusing on the first 4 variables: pressure, volume, amount, and temperature for the remaining ones. And in fact, for the first 4 equations. And in fact, on our first 4 equation, moles, our amount of gas, is going to be considered to be constant. So we're going to focus on those first 4 variables and give you a little bit of information about those. You're not going to have to write anything about these 4 until I tell you that it's time for notes again, so you'll take a brief break on this one. Okay, so pressure is the amount of collisions between particles in a gas. There are various things that can increase or decrease pressure, so the amount of room that a gas has, how much gas and particles are actually in a container, and then the temperature or energy also can affect the pressure of a gas. The volume of a gas is, of course, how much space it takes up. We typically are going to measure that in liters, and that's really important that you measure in liters when you use your ideal gas constant equation. But if you have a constant amount of a given amount of gas and you reduce the volume, you reduce the space, you're going to have more collisions of these particles, so you'll have a higher pressure. And then the more space it has, you'll have less collisions, so you'll have less pressure. Temperature is important in a gas because that also affects the spacing and the pressure. So when you have a high temperature, that is, remember that temperature is the average kinetic energy, so your particles are moving faster and spreading out more. And so you're going to have more pressure and more volume when you have a higher temperature. And then with a colder temperature, you're going to have slower moving, more closely packed together particles, and so you're going to have lower pressure and lower volume associated with a lower temperature. Moles, of course, are the amount of particles of gas, and as you imagine, the more gas you have, the higher pressure you're going to have as long as the volume is controlled in that, right? So the more there is, of course, the more collisions there are, and collisions equal pressure. So just a quick visual on those 4 constants or variables, and we're going to look and see how those variables play into our equations. So we have 5 total equations. The first 3 equations are dealing with when you're given 2 variables and you're trying to solve for a new condition of the same gas. The 4th equation, you're going to be given 3 variables and still solving for a new condition. And then the final one, our ideal gas law, is going to be you're given 3 variables and you're solving for that 4th variable. So again, you're given pressure, say volume in moles, and you're going to be solving for temperature or something along those lines. So let's look at our kind of easiest ones first. So we have Boyle's law, Char's law, and Gay-Lussac's law. Each one of those is dealing with 2 different variables. And when you're looking at the 2 variables, say with Boyle's law, pressure and volume, you're going to assume that the remaining variables, moles and temperature, are remaining constant. And so this kind of goes with that temperature image that we looked at the beginning. This is an inverse relationship between pressure and volume. So when pressure is high, you can see that the value for volume is lower. And then when the value for the volume is high, the pressure is going to be lower. And that corresponds with the image that we looked at earlier. So we have a large amount of space, we can have those particles spread out, so less pressure. We have a small amount of space, the particles are packed together, they collide more, so you're going to have higher pressure. So that equation there is P1 V1 equals P2 V2. What is 1 and 2? Well, that's the value that you start out with. So you're going to say, okay, I've got my gas at so many atmospheres of pressure and 6 liters of volume. If I switch the volume to 3 liters, what would the pressure be? So you'd be solving for P. So you get 3 out of the 4 variables provided for you, and then you just switch the equation around to solve for it. pretty straightforward algebra there. And Charles' law and Gay-Lussac's law are the same type of principles, just using different variables. Also, my last two laws are direct relationships. So here you can see volume and temperature go up together. So when you increase volume, temperature also tends to increase. When you increase temperature, volume tends to increase. And so that's kind of our little image we were looking at earlier as well. So that's a direct relationship. And when you have a direct relationship, that's going to be volume divided by temperature of your first value is equal for volume divided by temperature of your second value. So, and then finally, our last one is just pressure and temperature. And again, notice here when I'm increasing that temperature, I'm also increasing the pressure. And so that again is a direct relationship. As one goes up, so does the other. So it's a division problem. Our fourth equation is the combined gas law. So it takes all three of these principles and kind of applies them together. And so again, you would be given P1, V1, and T1, and P2 and V2, and usually you're just solving for T2 or one of the second variables. So you're typically solving for one variable, so you kind of switch around your equation as you solve for it. Again, these are assuming that moles and the amount of gas is constant. And I have given you the equations already switched around. So if you are trying to solve for those, then that's what the ideal gas law will look like switched around. So you can write those down in your notes as well. And then finally, we have the ideal gas law. So the ideal gas law is something that you'll see come back to you quite a bit. And this is PV equals nRT. So in this particular case, you're looking at pressure times volume is equal to moles times the gas constant times the temperature. And so in this equation, when you're using this, you're usually given the constant is something that you'll plug in and you'll be given that value. But you'll usually be given, say, volume, moles, and temperature, and you're solving for pressure, or pressure, volume, and moles, and you're solving for temperature, etc. So again, you can use algebra to turn those equations around, and these are rearranged based on basic algebraic principles. So you can write those down as well if you prefer to use in your notes in your practice problems later. It is really, really important that when you're using the ideal gas law that you are very specific in your units. So for example, if you are given milliliters, you have to convert to liters. If you are given degrees Celsius, you have to convert to Kelvin. So in the other equations above, as long as your values for these two are constant, so if you're starting with milliliters and you're ending with milliliters, or you're starting with Celsius and you're ending with Celsius, and in the previous equations, it's not as big of a deal. But in the ideal gas law, you absolutely have to convert to Kelvin and liters. Also, your pressure, there's 3 different units of pressure. And so in our other equations, you'll be given that unit of pressure and it's constant throughout, so you don't really have to worry about it. But in this, you are going to have to be aware of what unit of pressure you're using. So are you using atmosphere? So we've looked at STP, that's dealing with atmospheres, and 1 atmosphere is equal to 14.7 pounds per square inch. You don't really need to know that, but you might need to convert atmospheres to kilopascals or torr. And so you can do that. Or you can just use the different gas constant, which is kind of what I would suggest, because if you're asked For your solving, say, for pressure in atmospheres, you're going to want your answer to be in atmospheres. So you would use this number as your gas constant, 0.0821. That's your most common one that you'll find. But if you're given pressure in kilopascals, then your constant is, the value is going to change. That's 8.31. Or if you're given it in torr, or millimeters mercury, those are the same thing, then you will be using this number as your gas constant. So it's really important to make sure that you are paying attention to the unit that's being used in that question, and that you're answering in that unit, and that the gas law constant, your R value, is you're using the correct R value. So that's it for your notes. Hopefully you'll get those nice and filled out and work on your practice problems. You can work on them together, but you do need to have them totally complete by the time that I see you on Thursday.